In the depths of intergalactic space, hidden from the gaze of optical telescopes, Alcyoneus stretches across an almost unimaginable span of 16 million light-years. This vast structure, invisible to the human eye, reveals itself only when observed in radio wavelengths. Its true form is not a glowing spiral or a brilliant elliptical shape, but a pair of immense plasma jets, launched from the heart of a galaxy by a supermassive black hole. These jets, composed of relativistic particles spiraling through magnetic fields, light up the cosmos in radio waves, carving a colossus across the dark void. Alcyoneus is not just large, it redefines what astronomers believed was possible. Larger than any other known radio galaxy, it challenges current models of how such structures grow and evolve. The central engine, a black hole millions or even billions of times more massive than our Sun, feeds on gas and dust, and in the process, releases energy not just inwards but outwards, launching twin lobes of magnetized plasma. These lobes expand far beyond the visible boundaries of the host galaxy, interacting with the intergalactic medium and stretching through regions where galaxies are sparse and silence prevails. Despite its titanic scale, Alcyoneus resides in a relatively quiet cosmic neighborhood, far from the bustling cores of galaxy clusters. This isolation may be part of the reason it has grown so large. With little external pressure, its jets were able to expand freely for hundreds of millions of years. Its discovery only became possible thanks to advanced low-frequency radio observatories like LOFR, capable of detecting faint and extended radio emissions across vast swaths of the sky. This raised a new question: how many other giants like Alcyoneus remain hidden in plain sight, detectable only through their whispering radio echoes? The plasma streaming from its center carries information not only about the black hole's behavior but also about the environment through which it travels. By studying the structure and curvature of its lobes, astronomers can infer the density and turbulence of the surrounding intergalactic gas. In this way, Alcyoneus becomes both a monument to black hole power and a probe of the large-scale structure of the universe. Its presence suggests that the cosmic web, the filaments of dark matter and gas connecting galaxy clusters, plays a more active role in shaping these behemoths than previously thought. And still, the mechanisms behind such scale remain partially veiled. What allows a galaxy like this to maintain jet activity for so long? Why doesn't it burn out or collapse under its own energy output? These are questions Alcyoneus poses merely by existing. Its lobes, spanning distances that defy human comprehension, remain silent testimonies to the intricate ballet of gravity, magnetism, and cosmic time. Unlike quasars or blazars whose energetic outbursts are transient and often chaotic, Alcyoneus appears to embody endurance. Its jets, though ancient, are not remnants of a violent past, they are ongoing signatures of steady, long-lived activity. This suggests a finely balanced feedback mechanism between the central black hole and its environment, where just enough material is accreted to sustain the jets without overwhelming the host galaxy or exhausting the fuel supply too quickly. It's a cosmic marathon, not a sprint. One of the most remarkable features of Alcyoneus is the symmetry of its structure. Even across such staggering distances, its two radio lobes remain relatively aligned, implying stability in the orientation of the black hole's spin axis over hundreds of millions of years. In a universe filled with collisions, mergers, and disruptions, this level of coherence is rare. It hints at a remarkably tranquil galactic history, or perhaps at a black hole that has somehow resisted the chaos that typically reorients such jets. The environment surrounding Alcyoneus also seems peculiarly conducive to its growth. The intergalactic medium in its vicinity may be unusually low in density, providing little resistance to the expanding jets. This allows the lobes to extend without significant dissipation, making Alcyoneus not only enormous, but also unusually pristine in structure. Such conditions might be rare, making radio giants of this scale exceptional markers of special regions in the cosmic landscape. As technology advances and radio surveys deepen, more structures like Alcyoneus may be uncovered, but for now, it stands alone, the record holder, the ghostly titan. It challenges our understanding of scale and persistence in the universe. It forces us to ask how the quietest corners of space can hide the loudest relics of galactic activity. It invites new models of jet propagation, black hole feeding cycles, and cosmic evolution over billions of years. Alcyoneus teaches us that not all giants roar in light. Some whisper in radio silence, stretching arms of plasma across the void, sketching invisible lines in the dark fabric of the cosmos. These lines, traced by magnetic fields and relativistic particles, tell stories not just of their origin galaxies but of the unseen architecture of the universe itself, the places where matter, energy, and time unfold in vast, slow symphonies beyond human scale. These symphonies, composed by Alcyoneus and its kind, are not merely background noise in the cosmic orchestra, they are the deep bass, the long, slow rhythms that hold the structure of the universe together. While galaxies shimmer and dance in visible light, radio galaxies like Alcyoneus work silently in the dark, shaping and probing the intergalactic medium. Their jets inject energy into the vast void, heating it, stirring it, perhaps even seeding it with magnetic fields that span millions of light-years. In this way, they may influence the formation of future galaxies and the large-scale flow of matter across the cosmic web. At the core of Alcyoneus lies a paradox, an entity that devours matter to unleash energy. The supermassive black hole anchoring this galaxy is the fountainhead of its immense power, yet it remains invisible. It is the ultimate sculptor, chiseling jets from the raw material of space, but hidden behind an event horizon from which no light escapes. What we see are only the consequences of its presence, the twin jets of relativistic particles, the synchrotron radiation glowing in radio wavelengths, the vast lobes that grow like wings in the dark. This interplay of absence and power speaks to one of the great mysteries of the cosmos, how the most destructive forces can become the architects of creation on a cosmic scale. The plasma jets themselves are astonishing in composition and behavior. Twisting through magnetic fields, they exhibit turbulence, knots, and shock waves, signs of internal dynamics that remain poorly understood. Despite traveling at near-light speeds, they retain coherent structures across distances that dwarf entire galaxy clusters. This coherence implies a highly ordered launch mechanism near the black hole, where magnetic fields are tightly wound and focused, possibly through a relativistic accretion disk or a spinning ergosphere. The physics here dances at the edge of what we can currently simulate or even observe. But Alcyoneus doesn't only inform us about black holes and jets, it opens a window into dark matter. Since its radio lobes extend far beyond the visible matter of its host galaxy, they trace the shape and gravitational influence of the dark halo that surrounds it. These lobes, slowly drifting and curving, respond to gravitational gradients invisible to telescopes. They become tracers of the hidden mass that we believe composes most of the universe. Alcyoneus, in this sense, acts like a cosmic brushstroke painting an outline of the invisible architecture that binds galaxies and clusters together. Its scale also forces us to rethink the timeline of cosmic events. The formation of such enormous lobes is not the product of a brief flare-up or a singular event, it requires hundreds of millions, possibly billions, of years. This timescale is staggering. During the lifetime of Alcyoneus's jet activity, entire stellar populations may have risen and died within the host galaxy. Stars formed, went supernova, and seeded space with heavy elements, all while the silent expansion of radio lobes continued, indifferent and uninterrupted. This temporal layering makes Alcyoneus not just a spatial colossus, but a temporal one too, a monument to cosmic patience. And all of this unfolds in what, optically, appears to be a perfectly ordinary galaxy. This apparent contradiction, a visually mundane galaxy concealing one of the largest known structures in the universe, exemplifies the transformative power of multi-wavelength astronomy. Without radio telescopes, Alcyoneus would have remained undetected, invisible against the backdrop of space. But instruments like LOFAR, low-frequency array, revealed its hidden majesty. LOFAR's sensitivity to long wavelength, low-frequency radio signals allowed astronomers to detect the faint, diffuse lobes extending millions of light-years from the host galaxy. This discovery marked not only a triumph in observational technique but also a turning point in how scientists search for similar radio giants across the sky. The study of Alcyoneus has prompted new theoretical investigations into the factors that control the growth of radio galaxies. Previously, it was thought that powerful jets required dense environments, such as the rich cores of galaxy clusters, to amplify and confine their energy. Alcyoneus, however, appears to reside in a relatively sparse region of space, where the ambient pressure is low. This suggests that under certain conditions, isolation may be an advantage. With little resistance from surrounding gas, the jets can travel much farther, unimpeded by environmental turbulence. This insight may require astronomers to revise their models of radio galaxy evolution, accounting not just for energy output, but for environmental permissiveness. Another fascinating area of research concerns the role of magnetic fields. The radio lobes of Alcyoneus emit synchrotron radiation, which arises when high-energy electrons spiral around magnetic field lines at near-light speeds. By analyzing the polarization and spectral properties of this radiation, researchers can reconstruct the structure and strength of these ancient magnetic fields. These fields may have been amplified and shaped over hundreds of millions of years, providing crucial data on how cosmic magnetism evolves on the largest scales. Understanding these magnetic environments can shed light on everything from the behavior of cosmic rays to the dynamics of galaxy formation. Simulations have also begun to play a larger role in decoding Alcyoneus. High-resolution cosmological simulations, incorporating magnetohydrodynamics and relativistic physics, are now being run to replicate the conditions that might produce such a structure. These models attempt to recreate the full life cycle of a radio galaxy, from the ignition of a black hole jet to the slow inflation of radio lobes, and compare them to observations. Early results suggest that long-lived AGN, active galactic nucleus, activity, coupled with a stable spin axis and a relatively undisturbed galactic halo, could explain the observed features. But Alcyoneus remains a boundary case, a challenge to every model that seeks to understand cosmic extremes. Importantly, its discovery raises statistical questions. If such a massive radio galaxy has remained unnoticed until now, how many others might still be hidden? New surveys using next-generation instruments like the Square Kilometre Array, SKA, promise to map the radio sky with unprecedented detail and sensitivity. These telescopes could uncover thousands of faint, extended radio sources, some potentially even larger than Alcyoneus. Each new detection would help refine our understanding of galactic evolution, black hole growth, and the role of radio mode feedback in shaping the cosmos. The scientific value of Alcyoneus is thus far-reaching. It acts as a gravitational anchor point for future research, connecting observations with theory, individual galaxies with the cosmic web, and local environments with the deep past. It allows astronomers to test the limits of what black holes can do, how matter and energy interact in low-density environments, and how long-term processes can sculpt the largest known features in the universe. Alcyoneus also opens an intriguing dialogue between radio astronomy and cosmology. Its radio lobes act as cosmic weather vanes, subtly distorted by the gravitational currents of the large-scale structure of the universe. By examining the morphology, curvature, and asymmetry of these lobes, researchers can extract information about the density gradients and anisotropies in the surrounding dark matter. In this way, Alcyoneus serves not just as an astronomical object, but as a natural detector, a tracer of invisible scaffolding upon which the observable cosmos is built. This property is particularly valuable when studying the filamentary network of the cosmic web, the sprawling structure composed of dark matter, gas, and galaxies that permeates the universe. Alcyoneus, with its enormous span, likely crosses through one or more of these filaments, offering a rare opportunity to probe their composition indirectly. If one radio lobe appears slightly compressed or deflected, it may indicate interaction with a denser patch of intergalactic medium. Conversely, more diffuse regions may allow lobes to expand more freely. By combining these morphological clues with theoretical models and simulations, scientists can map otherwise invisible structures. Another active area of research concerns feedback mechanisms. The jets of Alcyoneus inject not just energy, but also momentum, magnetic fields, and relativistic particles into the intergalactic environment. This process, known as radio mode feedback, can heat surrounding gas, suppress star formation in neighboring galaxies, and prevent the cooling of hot intracluster plasma. Understanding this feedback is essential to galaxy formation theory, as it helps explain why many massive galaxies are quiescent. Their central black holes effectively sterilize their environments. Alcyoneus, as an extreme example of such feedback, offers a natural laboratory to study these effects over enormous timescales and spatial domains. Additionally, the radio lobes themselves may act as cosmic archives. As they expand, they entrap particles and fields from earlier epochs, preserving a record of the galaxy's past behavior. By analyzing the spectral aging of the synchrotron radiation, essentially measuring how the emitted radio waves lose energy over time, astronomers can reconstruct the history of jet activity. Was the black hole continuously active, or did it undergo cycles of quiescence and reactivation? Does the structure reflect steady feeding, or episodic eruptions spaced over eons? These questions are central to understanding the life cycles of AGN and their broader role in cosmic evolution. Moreover, the spatial orientation of Alcyoneus's jets might encode information about primordial spin alignment. In recent years, studies have suggested that the spins of supermassive black holes, and by extension their jets, may exhibit preferential alignments over vast scales, perhaps influenced by the initial conditions of the universe itself. If multiple radio galaxies like Alcyoneus are found with aligned lobes, it could signal a new layer of cosmic coherence, a bridge between galaxy formation and early universe physics. This would open a profound frontier, linking present-day observations with the quantum fluctuations that seeded structure shortly after the Big Bang. Finally, from a technological standpoint, the study of Alcyoneus pushes the limits of data processing and visualization. Its diffuse lobes required sophisticated filtering techniques to distinguish from background noise. Imaging such faint, extended structures demands careful calibration of radio interferometers and the development of novel algorithms to combine signals from hundreds of telescope stations. In many ways, the discovery of Alcyoneus is as much a triumph of data science as it is of astrophysics, showcasing how machine learning and high-performance computing now stand alongside telescopes in the astronomer's toolkit. The implications of Alcyoneus ripple outward not only across space, but also across disciplines. Its existence forces a re-evaluation of what constitutes a galaxy in the modern era. Traditionally, galaxies are defined by their stellar content, their morphology, and their place on the Hubble sequence. Yet Alcyoneus defies this categorization. Its most prominent features lie far outside its stellar core, in regions devoid of stars, gas, or optical structure. In this sense, it invites astronomers to think of galaxies not just as star islands, but as dynamic engines embedded in, and interacting with, the grander cosmic ecosystem. Instruments like LOFR, and soon the SKA, are reshaping this vision, revealing a radio sky filled with tendrils, lobes, halos, and filaments that are invisible in all other wavelengths. These radio components often tell stories of past violence, ancient outbursts, and the long-term influence of supermassive black holes, stories that cannot be read in starlight alone. Alcyoneus stands as a symbol of this transition, a gateway into a deeper, older, more invisible universe. The faintness of its radio lobes also raises questions about energy dissipation mechanisms. Over millions of years, relativistic electrons lose energy via synchrotron radiation and inverse Compton scattering with cosmic microwave background photons. That Alcyoneus remains visible at all suggests either a continuous or episodically refreshed injection of energy from the central engine. This phenomenon touches on the physics of jet stability, particle acceleration, and magnetocentrifugal launching mechanisms, some of the most complex and least understood areas of black hole astrophysics. As more data becomes available, comparative studies between Alcyoneus and other radio galaxies will offer valuable insights. Why did Alcyoneus grow so large, while others with seemingly similar black holes and environments did not? Is there a threshold, in mass, spin, or halo structure, that allows for such scale? Could subtle factors like black hole spin alignment with the galaxy's angular momentum or early cosmic conditions play a determinative role? Each of these questions represents a line of research that may unlock broader truths about the interplay between matter, energy, and spacetime. There is also the philosophical aspect, the humbling realization that such a giant could remain hidden for so long, unnoticed simply because we were not looking in the right way. Alcyoneus reminds us that the universe is vast not just in scale, but in dimension of perception. Every improvement in our instruments, every new wavelength we learn to observe, reveals another layer of reality. The visible universe is only the tip of a far larger structure, and every hidden Alcyoneus is a whisper from the cosmos urging us to listen more closely. Ultimately, Alcyoneus teaches us patience and scale, not just in kilometers or light years, but in time, complexity, and the quiet persistence of cosmic forces. It is a structure that formed slowly, evolved invisibly, and only recently stepped into our field of view, bearing messages from an ancient past. As we uncover more such giants, we will not only better understand galaxies and black holes, but also our own limited vantage, and the endless depths that remain unexplored. In the wake of Alcyoneus's revelation, a new generation of astronomers has begun to recalibrate their expectations. Where once the limits of galactic influence were confined to a few 100,000 light-years, this discovery shattered the conceptual boundary. A structure stretching 16 million light-years, more than 150 times the diameter of the Milky Way, is not just an anomaly, it is an expansion of the very idea of what a galaxy can become when unshackled by dense environments or energetic constraints. Ongoing observations are now focusing on the fine structure within the lobes of Alcyoneus. High-resolution radio maps reveal subtle variations in intensity and spectral index, suggesting a complex internal landscape shaped by turbulence, magnetic reconnection, and shock fronts. These features serve as records of past variability in jet power, environmental resistance, and even instabilities near the black hole itself. Each ripple in the plasma may correspond to a change in accretion rate, a shift in spin axis, or a gravitational interaction long past. In this way, Alcyoneus is not merely a static monument, but a living archive, inscribed with cosmic events in the language of magnetized plasma. The broader cosmological context is equally compelling. Alcyoneus may belong to a class of fossil radio galaxies, structures where the host galaxy has gone quiet, but the lobes persist for eons, slowly fading. If confirmed, this could help refine the timeline of AGN activity and the duty cycle of black holes. It also reinforces the concept of asymmetric aging, where a galaxy's visible and invisible components follow different evolutionary tracks. A seemingly inactive galaxy in the optical band might still be radiating immense energy across radio wavelengths, influencing its surroundings long after the central engine has gone dormant. In terms of methodology, Alcyoneus has inspired new search strategies. Rather than looking for bright, compact radio sources, astronomers are now developing algorithms to detect extremely faint, low-surface brightness structures across wide areas. These techniques rely on subtracting noise patterns, stacking data, and enhancing diffuse emission signatures, computationally intensive, but increasingly effective. These methods are not only yielding candidates for new giants, but also uncovering intermediate-scale relics that fill in the evolutionary gap between ordinary radio galaxies and ultra-extended ones like Alcyoneus. Alcyoneus has also become a touchstone for educational and public science communication. Its immense scale provides an intuitive and awe-inspiring example for illustrating astrophysical concepts, from black hole jets to cosmic magnetism, from relativistic particles to the structure of the universe. When people hear that a galaxy can stretch for 16 million light-years, it challenges their sense of scale, time, and possibility. It invites not just curiosity, but wonder, the same wonder that has driven science since ancient times. In this sense, Alcyoneus is more than data. It is a mirror held up to our cosmic ignorance and our technological potential, a reminder of how much we have yet to see. As we build more sensitive arrays, as we refine our methods, and as we extend our vision into frequencies never before explored, more giants will awaken from the dark. Each will carry its own secrets, but all will share a common trait. They speak of cosmic endurance, the slow but unstoppable unfolding of energy and structure across the deepest reaches of time and space. In the pursuit of uncovering more giants like Alcyoneus, astronomers are not only scanning the sky, they're rewriting the theoretical frameworks that govern jet propagation, black hole fueling, and galactic ecosystems. One key question now being explored is how cosmic filaments and voids might guide or constrain the growth of radio lobes. Since the cosmic web is composed of an intricate network of dark matter and diffuse gas, it can subtly steer or stretch structures like those of Alcyoneus, shaping their evolution in ways previously underestimated. In this context, Alcyoneus is not an isolated oddity, but a participant in the choreography of the universe's large-scale geometry. To test these hypotheses, researchers are correlating radio galaxy orientations with the known topology of the cosmic web derived from galaxy redshift surveys. Early results suggest that in some regions, radio jets do indeed align preferentially along filamentary axes, implying a coupling between black hole spin and cosmic structure. If Alcyoneus aligns with such a filament, it would strengthen the idea that galaxies and their central engines are not randomly oriented, but are instead embedded in a gravitational and magnetic infrastructure far grander than themselves. Meanwhile, deep learning tools are beginning to play an unexpected role in the next phase of exploration. Trained on thousands of radio images, neural networks are becoming adept at identifying ultradiffuse radio lobes, even when they are buried in noise. These models are uncovering a growing population of hidden giants, which, though not as large as Alcyoneus, still defy previous expectations of galactic scale. As these tools evolve, it may become possible to automatically reconstruct the life history of radio galaxies from their morphology alone, a kind of astroforensics powered by artificial intelligence. Alcyoneus also feeds directly into high-energy astrophysics. The jets and lobes it produces are potential sites for ultra-high-energy cosmic ray acceleration, possibly reaching energies beyond those achievable in Earth's most powerful particle accelerators. Understanding how such particles are energized and confined within the lobes could help solve one of the most persistent mysteries in astrophysics, the origin of the highest energy particles observed striking Earth's atmosphere. Alcyoneus, in this sense, becomes a natural accelerator, a laboratory spanning millions of light-years in which exotic physics plays out over incomprehensible durations. Moreover, these immense jets may act as conduits for chemical enrichment, distributing metals and relativistic particles far beyond the boundaries of the host galaxy. Over time, this feedback could influence star formation in neighboring systems, or even in small satellite galaxies caught in the path of the expanding lobes. In this way, Alcyoneus becomes not only a relic of black hole activity, but also a sculptor of the intergalactic environment, a bridge between isolated galactic processes and the shared history of cosmic evolution. As for the host galaxy itself, it is surprisingly unassuming. A standard elliptical, neither particularly luminous nor peculiar in structure, it offers few clues that such a colossal force resides within. This incongruity highlights a critical point: appearances in astronomy can be deeply misleading. The most extraordinary phenomena may lie beneath the surface, detectable only through careful observation in unconventional wavelengths. Alcyoneus reminds us that the universe often hides its most magnificent structures not behind clouds or distance, but behind frequency, in wavelengths we once ignored, and now must learn to embrace. The silence of Alcyoneus' invisible light underscores a profound lesson in modern astronomy: the cosmos is multi-layered, and each wavelength unveils a different truth. For centuries, human eyes, limited to the narrow band of optical light, constructed a partial vision of the universe, missing vast phenomena that whisper rather than shine. Alcyoneus is one such whisper, its radial lobes stretching across the abyss with a quiet that belies their enormity. They are not luminous like stars, nor explosive like supernovae, but they are enduring, persistent, and immensely powerful in their own domain. The question of why Alcyoneus grew so large continues to motivate multidisciplinary studies. One emerging theory suggests a combination of factors: a high-spin supermassive black hole, a long-lasting supply of low angular momentum gas, and a quiet intergalactic environment. Such a trio could allow the central engine to sustain stable, collimated jets for billions of years, unimpeded by disruptions like mergers or turbulence. These conditions are rare, but not impossible, and Alcyoneus may simply be the cosmic equivalent of a tree that found fertile ground and was left alone for eons to grow. Furthermore, the age of its lobes is now under active investigation. Using spectral aging techniques, which rely on the predictable energy loss of electrons due to synchrotron radiation and inverse Compton scattering, astronomers can estimate the time since each region of the lobes was energized. Initial estimates suggest ages on the order of several 100 million years, if not more. This makes Alcyoneus one of the longest-lived jet systems known, surviving not only its own active galactic nucleus phases but also large-scale cosmic evolution, including the drift of galaxy filaments and the expansion of the universe itself. In upcoming years, telescopes like the Square Kilometre Array, SKA, and Unveiling, Next Generation Very Large Array, are expected to reveal many more such systems. With vastly improved resolution and sensitivity, they will allow scientists to trace jet lobe interactions with surrounding gas in unprecedented detail. This may help resolve long-standing mysteries about jet stability, entrainment, and energy transfer on cosmological scales. Alcyoneus, then, becomes the benchmark, the giant against which others are measured, the first of a new class of galactic leviathans. It also raises tantalizing cosmological questions. Could such large-scale radio structures affect measurements of the cosmic microwave background, CMB, through subtle anisotropies? Could their relic particles influence the thermal history of the universe's diffuse gas? Could they help explain the so-called missing baryons, the normal matter predicted to exist, but still undetected in large quantities? If Alcyoneus-type structures are more common than we think, they may account for unseen reservoirs of mass and energy shaping cosmic evolution behind the scenes. From a human perspective, Alcyoneus invokes humility. It exists entirely beyond the reach of our senses, its presence betrayed only by the artificial ears we've built to listen to the universe's longer wavelengths. And yet, it was always there, expanding, radiating, evolving, long before our species ever peered into the sky. In this sense, Alcyoneus is not just a discovery. It is a revelation. It tells us that the universe still holds secrets of staggering proportions, awaiting only the patience, curiosity, and ingenuity to uncover them. Alcyoneus also beckons a new era of astrophysical synergy, a fusion of observational radio astronomy, theoretical modeling, cosmic magnetohydrodynamics, and even particle physics. As its colossal lobes ripple through the intergalactic medium, they provide natural laboratories for studying plasma behavior under extreme, long-duration conditions. The lobes consist of collisionless plasma, a regime where particles interact more through electromagnetic forces than direct collisions, akin to conditions found in the early universe, in solar flares, and in particle accelerators. Understanding how this plasma propagates, cools, and interacts with the surrounding medium has implications far beyond galactic astrophysics. It ties into universal plasma behavior across vastly different scales. The interaction between the expanding lobes and the surrounding intergalactic gas also initiates shock fronts, which may compress and heat the medium. These shock waves can be subtle in low-density environments, but over millions of years, they can gently stir otherwise quiescent regions of space. Such shocks may trigger star formation in distant, diffuse gas clouds or suppress it through heating, illustrating again how Alcyoneus, though seemingly remote, may influence galaxy evolution on a wide scale. It becomes not just a passenger in the cosmic web, but an agent of change, invisible, but impactful. There's also growing interest in relic radiation, low-frequency radio emissions from long-dead AGN lobes that persist for eons. Alcyoneus may be a hybrid of a currently active nucleus and relic lobes, or perhaps it is in the late stages of activity, transitioning into dormancy. If so, its spectral signature may encode this transition. Scientists now use broadband radio observations to track such changes, analyzing the curvature of the synchrotron spectrum to determine whether fresh high-energy electrons are still being injected, or if the system is coasting on its last bursts of momentum. Meanwhile, its role in magnetizing the intergalactic medium cannot be overstated. As its lobes swell and dissipate into the surrounding void, they carry with them tangled magnetic fields, potentially enriching the cosmic web with large-scale magnetism. The origin of cosmic magnetic fields is still an open question. Some may be primordial, others generated by galaxies and ejected over time. Alcyoneus, through its gentle but relentless expansion, likely contributes to this magnetic seeding, acting as a cosmic pollinator across millions of light-years. For those studying black hole spin, Alcyoneus offers another clue. Only fast-spinning black holes can sustain highly collimated, powerful jets for extended periods, especially on the order required to generate 16 million light-year structures. This supports the notion that spin energy, rather than just accretion energy, plays a major role in fueling long-lived jets. Such systems may tap into the Blandford-Znajek mechanism, extracting rotational energy from the black hole via magnetic field lines. In this view, Alcyoneus becomes a testament to the efficiency with which nature can extract energy from rotation, like a cosmic dynamo running on spacetime itself. And still, despite all this, Alcyoneus is quiet. No brilliant flare announces its presence. No supernova or gamma-ray burst flashes from its core. It simply exists, vast, ancient, slow, and steady. It is a reminder that not all cosmic drama comes in bursts. Some is written in silence. Some is told in the invisible language of low-frequency radio waves. Some unfolds not over seconds, but over hundreds of millions of years, and still leaves traces we can study today. Alcyoneus, in its silence and scale, subtly redefines the parameters of cosmic narration. In an era dominated by transient phenomena, explosive supernovae, flickering quasars, fast radio bursts, it is the slow epics like Alcyoneus that remind us the universe is not only a theater of sudden events, but also a vast canvas of processes that unfold in geological, even cosmological time. Its lobes are not mere byproducts of black hole activity, they are time-engraved sculptures of energy, matter, and magnetism, drawn across space by the steady hand of relativity. This realization reframes the role of galaxies as dynamic entities within the cosmic web. Where once galaxies were treated as isolated islands of stars, Alcyoneus shows that galactic influence can extend deep into intergalactic space, modifying conditions in regions far removed from stellar nurseries or dark matter halos. Such influence isn't dramatic, it's osmotic, persistent, a quiet reweaving of the intergalactic medium through the slow exhalation of magnetized plasma. The interplay between kinetic energy and entropy in this context is now a subject of theoretical interest. As Alcyoneus expands, it injects order into surrounding gas through collimated jets, but those jets eventually dissipate, transform, and heat the medium, increasing its entropy. This conversion of directed energy into thermal background parallels processes thought to have occurred during the epoch of reionization and even inflation in the early universe. Thus, Alcyoneus becomes a small-scale analog of universal thermodynamic flow, bridging microcosmic and macrocosmic physics. Another frontier inspired by Alcyoneus is the study of intergalactic voids, the vast regions between filaments where galaxies are sparse or absent. Because the lobes of Alcyoneus may drift through or terminate in such voids, they offer one of the only natural probes of these regions. Their shape, energy profile, and curvature may reveal previously inaccessible information about void density, residual gas pressure, and the properties of dark energy acting on large-scale structure. In this way, Alcyoneus transitions from being an object in the universe to being a measuring instrument of the universe itself. Astrobiologically, Alcyoneus even raises philosophical questions. If complex life depends on the long-term stability of planetary systems and low radiation environments, then galaxies like Alcyoneus, with jets extending millions of light-years, could either sterilize vast regions or create protected zones depending on their orientation and energy output. Could there be planets in orbit around stars in the path of ancient radio jets, slowly bathed for eons in low-level radiation? Might such exposure alter the chemistry of atmospheres, or even the rate of evolution? These remain speculative, but underscore the interdisciplinary reach of objects like Alcyoneus. In many ways, Alcyoneus is a Rosetta Stone for radiocosmology. Its extraordinary size, faintness, symmetry, and persistence challenge assumptions across multiple domains: black hole physics, jet dynamics, intergalactic medium composition, cosmic magnetism, and even the topology of spacetime. It is an object that speaks every dialect of astrophysics at once: plasma physics, thermodynamics, general relativity, high-energy particle theory, and large-scale structure. And its voice, paradoxically, is a whisper. In the final analysis, Alcyoneus is not just a discovery, it is a paradigm shift. It alters what we look for, how we look for it, and what we assume is possible. It is a testament to the quiet giants of the universe, the slow burners, the silent sculptors, the unseen engineers of cosmic architecture. It reminds us that some of the greatest forces in nature are not those that flash, but those that persist. The legacy of Alcyoneus is just beginning to unfold. Future missions and observatories, such as the Square Kilometre Array, SKA, promise not only to detect more giants like Alcyoneus, but also to capture their detailed evolution over cosmological epochs. With such exquisite sensitivity, these next-generation radio telescopes will unveil the subtle internal structures and magnetic topologies within Alcyoneus's immense lobes, revealing the intricate interplay of turbulence, shocks, reconnection, and particle acceleration. Indeed, from a theoretical standpoint, Alcyoneus poses vital questions about the physics of magnetic reconnection and relativistic turbulence occurring at extraordinary spatial scales. Within its lobes, high-energy particles interact with chaotic, dynamically evolving magnetic fields. Understanding these processes better will feed back into plasma physics, informing research not only in astrophysics but also fusion energy and laboratory plasma confinement. Alcyoneus thus becomes a natural astrophysical laboratory, pushing the boundaries of fundamental physics into new realms. Meanwhile, advanced cosmological simulations incorporating magnetohydrodynamics, MHD, and particle-in-cell, PIC, modeling are beginning to replicate the conditions that created Alcyoneus. These computational models allow scientists to run controlled experiments on black hole jets and their evolution over billions of years, something impossible to observe directly. By comparing simulation outcomes with observational data, astronomers hope to pinpoint the precise environmental conditions and physical processes required to form giants of Alcyoneus's caliber. Moreover, Alcyoneus's sheer longevity challenges the current theories of galaxy black hole coevolution. Typically, active galactic nuclei, AGN, cycles, periods when central black holes are actively feeding and producing jets, are considered transient, lasting tens of millions of years. Alcyoneus forces astronomers to reconsider whether certain galaxies can remain quietly active, sustaining low-level accretion and steady jet production far longer than current models anticipate. Could there be subtle, previously unrecognized mechanisms that maintain stable accretion rates at very low levels? If so, Alcyoneus provides a crucial case study for these processes. There are also fascinating considerations about gravitational dynamics. Alcyoneus, spanning such immense distances, inevitably responds to subtle gravitational perturbations from neighboring galaxy clusters, dark matter overdensities, and cosmic filaments. Mapping subtle distortions in Alcyoneus's lobes could thus yield insights into the large-scale gravitational fields permeating intergalactic space. It becomes not only an astrophysical marvel, but also a gravitational probe that reveals details of the universe's hidden mass distribution. As observational data grow richer, astronomers may even uncover smaller galaxies or gas clouds trapped within Alcyoneus's lobes, satellites swept along in the wake of these giant plasma structures. Such intergalactic hitchhikers could provide unprecedented insights into how galaxies and gas structures interact with highly energetic environments. They may also help measure the lobe's precise energy content, density structure, and magnetic field strength through their gravitational interactions and internal dynamics. Finally, Alcionius has become an emblem of astronomical storytelling, an inspiring reminder that some of the universe's greatest wonders do not loudly announce themselves. Instead, they wait patiently in the shadows, whispering their presence through subtle signals, gently encouraging humanity to extend the senses far beyond the familiar and the visible. Alcionius reminds us that exploration is not merely about brighter telescopes, but about broader vision, curiosity, and the humility to recognize how limited our perceptions have been. As Alcionius continues to unfold its secrets, scientists stand poised on the edge of discovery. Each new finding adds a sentence to a cosmic biography spanning millions of years, composed not of dramatic flares, but of quiet persistence. It is this persistence that makes Alcionius extraordinary, a gentle titan, quietly sculpting the invisible architecture of the cosmos. In the end, Alcionius invites us to shift our gaze from transient spectacles toward the quiet masterpieces of cosmic time. It is a lesson in humility, revealing that our most advanced telescopes have only begun to probe the hidden, silent giants that shape the cosmos. Its discovery signals not an endpoint, but a beginning, the threshold of a new era where radio astronomy, theoretical physics, and computational science unite to unveil structures far beyond human imagination. Alcionius is more than just a record-setting galaxy. It is a cosmic paradigm, a reminder that profound wonders often lie hidden, invisible yet influential, patiently awaiting the moment we dare to listen. As we continue to refine our instruments and expand our understanding, Alcionius stands as a silent guardian at the edge of discovery, whispering gently that the universe's greatest stories are not always told in brilliant bursts of light, but sometimes quietly and persistently, across the silent echoes of space and time.